Hi guys, so I wanted to review the types of bonds. So we had our weakest bonds were hydrogen bonds, and those were between water molecules. So we had an oxygen here and two hydrogens. So this is actually kind of a complex atom. So we want to look at oxygen individually, which has 8 protons and 8 electrons when it's in its periodic table form. And then if you want to write the lower number, you would have 8 neutrons if you were going to draw them out. So you would take 16 minus 8 and you would get 8 neutrons. So 8 protons with the matching 8 electrons. So our first ring has 2, and then our second ring has 6 left. So 8 minus 2 would be 6. Here we go. 1, 2, 3, 4, 5, and 6. And 6 is 2 away from happy. So we want 2 more electrons. And so what happens here is that our hydrogen atom, so hydrogen is just 1, 1. So since it has just one ring, it can only fit the 2. So it actually wants 2 electrons, but it only has 1. So our hydrogen is going to come up here and overlap its orbital and contribute its electron, so that that electron is now shared around the hydrogen, but it's also shared around the oxygen. So this bond right here is a polar covalent. So polar means charged, and it's unequally shared. So that electron that the hydrogen contributed doesn't get to spend just as much time around the hydrogen as it does around the oxygen. It's actually pulled towards the oxygen because the oxygen is very electronegative. So it's like an electron sucking magnet. So it's pulling those electrons, both the one that it contributed and the one that was contributed by the hydrogen. They're holding closer to the oxygen atom than they are to the hydrogen. But the hydrogen is still happy and happily bonded. So that will happen again over here because 6 was 2 away from happy, so it needed to make 2 bonds. So we're going to put another hydrogen right over here. And so this is another polar covalent bond. So just to point out, those 2 dots are electrons, but it can also be drawn as a bar. So this electron is going to travel around here and then around here, and this electron is going to travel around here and around the oxygen. So it is always going to make it unevenly shared, so polar covalent bond, but their orbitals are overlapped, so it's a strong bond called a covalent bond. But between these molecules of water, so H2O is water, we will have bonds that occur because of a slightly positive charge formed on the hydrogens, because those electrons aren't really balancing out the proton that's inside of it because it's pulled closer to the oxygen, so it's leaving the hydrogen slightly positive and creating a slightly negative charge over on the opposite side. So we want to make sure that we get our charges correct. So if it's kind of deficient of an electron, then we have a positive charge, and if it's gaining a bit of an electron, it's not a full charge. They didn't like steal the whole electron. They're just kind of hoarding it a little. You're creating a slightly negative charge at these poles. So the slightly negative charge, we draw it with dots, is going to be attracted to the slightly positive charge on the hydrogen atom. So this slight positive charge is going to attract the slight negative charge, and by drawing it dotted, we are saying this is a weak and transient bond. So hydrogen bond is epic and amazing, and we love them because it gives water all the amazing properties that it has. So we do want to review those properties. So things like high surface tension or cohesion. So that means that water really sticks to water really, really well because it's making all of those hydrogen bonds off of each one of its molecules. So that allows for water to stick to water very well. So that is cohesion. Adhesion is that water also sticks to other compounds. So sticking to something else. So it kind of clings. So that allows capillary action to happen. So up in plants, the water is sticking both to the plant and it's also sticking to itself so that we can pull it up these long narrow tubes. We also have a wonderful solvent effect. So it gets along with all other charged ionic solutions. So anything that's polar or ionic is going to dissolve in water and get along with water quite well. It doesn't heat up or cool down very rapidly, so that's nice. That's called a high specific heat, and that keeps Earth, functioning properly, and it also helps even just individual bodies stay thermoregulated so that we can keep sort of a constant temperature and a very narrow range of temperature variation, and that's mostly due to water. It being a good solvent also makes a lot of chemical reactions able to happen because everything dissolves in water. So we are mostly made of water, so that's cool. So most of our blood is actually water, and our cells are full of water, and so we're pretty much water. Other important things. So that ice is less dense or floats is because of these hydrogen bonds. So they become rigid and hold the molecules of water apart, so that ice that you would think when things freeze, they would get closer together, all those bonds would shorten and it would get heavier. But because it has all these hydrogen bonds, it allows it to stay sort of spread out. And so we see that like light flaky snowflakes fall, and you can see the crystalline structures there. It's very beautiful, but it also keeps our icebergs from sinking, and our iced tea from, having ice cubes drop down. But if all of the icebergs did sink, that would change life on Earth. We would just be an aquatic planet, so we wouldn't have land masses that were above water, which is interesting too. It's also a good buffer, so I'm not sure we covered that one. But the fact that water has hydrogens and OHs kind of makes it a perfectly balanced molecule. So acidic properties have H pluses, and OHs are alkaline. So when we put them together, we can see that we have like the perfect neutral property at a 7. So it's really interesting. Water is so perfect and beautiful. Okay, so that is hydrogen bonds. We want to cover, we kind of covered covalent bonds in there. So covalent bonds can be polar or non-polar. So covalent are the polar ones that we just used in our example. So oxygen was unequally sharing those electrons with the hydrogen. So it was pulling them closer to itself. So this bond right here is unequally shared, right? So we want to note that a polar bond, a polar covalent bond between two atoms, so here it's O and H, they overlap So that's a very important feature, that those electrons are actually in that valence shell, but those valence shells overlap. So that's how you would sort of note the strength of that bond, is that those orbitals are actually overlapping, but it's unequally shared. So again, that means charged, or that there's an electron imbalance, like the charges of positive and negative are not equally canceling out. Okay, so but then we can have nonpolar. So what would a nonpolar example be? Well, if an atom is basically as electronegative as the one it's sharing with, then carbon is a good example. So if carbon and carbon share a bond, you would have no more pull from this carbon atom than you would from this carbon atom. So this is a perfectly centered bond. So that would be a non-polar covalent bond. And if you want to draw that out perfectly, I'm just going to do one of the covalent bonds that would be off of this molecule. So we have carbon 6, 12. And so to draw these 6 protons balanced out with 6 electrons, we have our first shell, which can only hold 2, and then we have the outermost shell or valence shell that has 4. So that actually means that it's 4 away from happy, because we want 8 in the outermost shell. And I'm only going to draw one of these bonds right now just to show that we also have a carbon 6, 12 over here. So we put 2 of those electrons in the first shell, and then the second shell is going to overlap and share this electron. So this electron is coming from this carbon atom, but it's rotating around both of them. This carbon atom is contributing this electron. It's going to rotate around both of them. So you have overlapping clouds of electrons, and that is a covalent bond. But this one is equally shared, so it is not charged. So to make these atoms completely happy, we would have to bond with something else. So we could add a hydrogen atom here if we wanted to just show that we would have 3 more bonds to complete that atom. And we would do the same thing on the other side. But again, these are non-polar covalent bonds, and even carbon is not that electronegative, so it doesn't really pull these electrons in closer than equally sharing with the hydrogen. So this is a non-polar atom, and that means non-charged, and it also means that it doesn't get along with water, so it's hydrophobic. So anything that's non-charged or non-ionic or non-polar, all of those words are kind of interchangeable. All of those are hydrophobic or water-fearing or water repellent, like water repelling. Water does not get along with them at all. So if you want to just imagine, like, you smear a whole bunch of butter on a table and then you put water on top, you can see that the water just kind of clings to itself and is repelled away from the lipid or the fat. So that is a covalent bond that is nonpolar versus a polar covalent bond. So water gets along with water just fine. So hydrophilic is the word there. So we did hydrogen bonds and covalent bonds, and now we're just going to do an example of ionic bond. And our classic example is NaCl, so sodium chloride. So we'll just try to draw that here. We have sodium with 1123, and the chlorine is going to start off with 17. So again, we don't really have to include the atomic mass, I just usually do. So let's start with 11 protons, means that it's also going to have 11 electrons to balance it out. So we start with 2, and then we have 8, so we have a full shell, so 8 plus 2 equals 10, so we still need one more, so we have one more shell with just a single electron. So that's 7 away from happy. So we would have to make 7 bonds to complete that shell, and it's like carrying a lot of luggage if you have to hold on to that many atoms surrounding it. So instead, it just gets rid of that and goes back to its complete shell down here, so that it's happy with its structurally sound 8 in its ring. But just to count that out, we had 11 protons, and then we did have 11 electrons, so that would be neutral. But we got rid of one of those electrons, so we have 11 protons, but now we only have 10 electrons. That leaves one extra positive charge, so this becomes a cation. So cats are positive. You can imagine that T as a plus sign, or somebody said protons are positive. Isn't that cute? So you can be punny too. So cats have pos, and cation is positive. Okay, so then we also have the chloride ion. So we want to start counting out. This is 17 positive protons balanced by 17 negative electrons. So we have 2, then we have 8. So that makes us at 10. So we still have 7 left we need to account for. So we can just write the number 7 if you want to. But then we get to positive by accepting this electron from the sodium ion. So the sodium ion is going to just jump ship. It actually leaves the atom. These orbitals are not overlapping. It just completely chucks it, goes back to its stable 8 in its second shell, and this one gladly accepts it so that it's stable, but then it becomes a negative ion. So a negative ion. So a negative ion is called an anion. And you can memorize that however you would like, but this negatively charged ion is now perfectly stable because it has 8 in its outermost shell, which makes it happy. But a positive attracts to a negative, just like a proton attracts to an electron. So a proton and an electron are drawn to each other. That creates this ionic bond. So it's not a full overlapping orbital, but it is a full positive charge attracted to a full negative charge. So this is a bond. So sodium chloride is table salt. So we just created salt, and we know that it's charged, so it gets along with water. So water loving. And we also know that we've probably, made soup or put salt in water at some point. Maybe you're just gargling water to try and get rid of a sore throat. But we know that salt dissolves in water because it is a charged molecule. So you will have a weaker bond. So if there were another chloride ion over here, this sodium ion would be equally attracted to this chloride ion as it is to every other one. And the same goes for a chlorine. If there was another sodium plus over here, they're all just kind of transiently attracted to all the other negatively charged atoms. So it's not a strong bond. So if we put these bonds in order, we would say that covalent bonds are strongest because they're actually overlapping. And again, just to review, we had polar, where the charges or the electron is shared unequally, and we had nonpolar. So those bonds are equally strong. And then we have ionic, and that was one fully positive electron attracted to a fully negative. So this bond is like medium strength, but your orbitals are not overlapping. And then we had hydrogen bonds, which are our weakest. So it wasn't a full charge of positive attracting a full negative charge. It was a partial positive attracting a partial negative. The thing that makes that so amazing for water is that each molecule of water would make multitudes of these bonds. So we would have basically like 4 hydrogen bonds to every molecule of water. And so we would they have all those amazing properties of water because there's just so many hydrogen bonds. But they are also meant to be unzipped. So one of the famous hydrogen bond areas is actually in our DNA. So all of these are hydrogen bonds that are the rungs of the ladder. And DNA is meant to be zipped and unzipped. So we have that example there. Okay. I think that is a long enough video to review the bonds. So I will pause there. So I'll be back with you in a little bit, guys.